So it's a great pleasure to be back to Natal, and glad to see you all here, not at the beach. And I see we have a tense program, so let's see if attendance stays high till the end. So I've been asked to speak about a topological Kondo effect. To understand the topological Kondo effect, we need to first understand what are Majorana fermions or Majorana bound states. So in my course, in the first part, which will roughly be the lecture today, I will speak about the basics, introduce what are Majorana fermions, what are Majorana bound states. In the second part, probably tomorrow, maybe I'll start also a bit today, we will discuss how you can realize Majorana fermions in the lab. There is now quite some evidence that people have already seen it. Wouldn't call it a proof, but the evidence is really mounting, and we will discuss these proposals in nanowires. In the third part, we will then look at how we can really play non-local games with these Majorana fermions, in particular by coupling the Cooper pair dynamics to the dynamics of Majorana fermions through Coulomb charging effects. This can be done very easily, at least in theory, if you have a floating device, so not a grounded device. In that case, you will have Coulomb charging energies, so capacitive effects that charge this device, and that will help us here. And that will then bring us to the topological Kondo effect, which is a generalized Kondo effect, so the interaction of a spin-like impurity degree of freedom, which is coupled to leads and basically enters a highly entangled state at low energies. And this is, I think, the only version of an overscreened multi-channel Kondo effect, which exhibits non-Fermi liquid behavior and is predicted to be really stable against anisotropies. That's usually the problem with these multi-channel Kondo type proposals, that if you have any kind of deviation from isotropy, you can easily destabilize it. If time permits, in the fifth part, I will focus on some recent developments, but that's really optional depending on how quickly I move. And I encourage you to just stop me if I'm too fast, ask questions, and whatever do to keep me slow. Originally, I was planning a Blackboard presentation, but Pasquale told me there will be no nice Blackboard, so that's why I prepared PowerPoint, but I'll try to be as slow as with PowerPoint. If you want to read more, there's an excellent review by Jason Alicia from 2012. In fact, I used some of the pictures in my slides from this review. He basically gives many, many details and summarizes the state of the art by 2012. Somewhat more easier to read and less extensive reviews are by Lainze and Flensburg and by Carlo Benacker. And finally, the last paper by myself in collaboration with Alex Sassunov and Alex Altland describes the details of the topological Kondo effect, to which we will come later. Okay, so let me start with part one, introduction to Majorana fermions and Majorana bound states. So we will try to answer these questions, and I hope after my course you will be able to say at least a few words to each of these questions yourself. So what are Majorana fermions or Majorana bound states? How can we describe them mathematically? How could they be realized in the lab? And what properties do they have? And finally, why should we care? Okay, so the first question is, what are Majorana fermions? And in one sentence, a Majorana fermion is a fermionic particle that is its own antiparticle. Yeah, so particle that its own antiparticle. For bosons, that's a common theme. Photons, they are just their own antiparticles. For fermions, this is a much less trivial statement. So in a second quantized notation, you would say if I have a creation operator that creates this particle, it should be equal to its own annihilation operator. Yeah, so these fermionic creation and annihilation operators should be equal. because particle equal antiparticle means the charge is equal to minus the charge should be 0. So this Majorana particle should be neutral. Majorana originally in the 1930s constructed it as a real valued solution of the relativistic Dirac equation. And he had in mind that some elementary particles could be Majorana fermions. So these type of Majorana fermions are dispersive particles, really modes, while the Majorana bound states that are the main part of my talk are bound states that are basically localized in space. One still calls them Majorana fermions, but one should be a bit careful that this is not the same. Yeah? So these particles were suspected by Majorana to be describing neutrons. By now we know neutrons are not Majorana fermions, but with neutrinos the business is still not settled. At least to my knowledge, experiments are still unclear. The way to look for this experimentally is in double beta decay. So in a normal beta decay, a neutron decays into proton, electron, and an antineutrino. And now if you have two such processes, so double beta decay, and the neutrino is equal to the antineutrino, then they can annihilate. And that means in the outcoming emission rate of neutrinos, you should see a decrease. So if there is a decrease in the emission probability of neutrinos, that is a clear signature for Majorana character of these particles. So that's in elementary particle physics. Here we are looking for Majorana fermions as emergent quasiparticles in condensed matter. Yeah? Just like a quasiparticle in Fermi liquid theory is built up from excitations of a system of 10 to the 20 or 10 to the 30 electrons, but it's still a good excitation in the sense that it doesn't decay, or its decay rate is very, very small at low energies. Yeah? So in that sense, these can be stable excitations, emergent excitations, but of course they're not elementary particles. So to make you aware of the difference to standard fermions, let me briefly recapitulate how we describe these standard fermions in a second quantized framework. So for instance, let's just take one orbital state of an atom. Yeah? So we have our atom. One single particle state you can fill according to Pauli's principle by either 0 or precisely 1 electron. So this gives you two eigenstates, 0 and 1, the empty and the fill state. And now in second quantization, you introduce a fermion operator, C-dagger, that creates a particle. So by acting with it on the state 0, you will end up in the filled state. And likewise, the adjoint C annihilates a particle. If you act with it on the empty state, you simply kill the whole state, so nothing remains. We should carefully distinguish this 0 is just nothing from the vacuum state, which is the empty state. On the other hand, if you act with C-dagger on the filled state, it will also kill this state, while acting with C on 1, you just go back to the empty state. Yeah? And these rules are nicely captured by the algebra. So you have C-dagger plus C-dagger C, the anticommutator, equal to 1. Unlike the bosonic one, where you have a commutator with a minus. And likewise, you have such relations for fermion operators themselves that implies that C square is 0. So acting twice with an annihilation operator just kills everything. So that's the Pauli principle here. So we can also say that this operator C annihilates a particle, or equivalently, it creates an antiparticle. And in condensed matter, typically an antiparticle is called a hole. Yeah? So we have electrons and holes. And these particles we can nicely count with a Hermitian operator n. C-dagger C, that's the occupation number operator. You see it's Hermitian. So its eigenvalues are real. If you square it, n square is just equal to n. That follows by using these rules. And so the eigenvalues have to obey also this equation, and there are just two roots of this equation, 0 and 1. So that's the standard picture. Now let's try to see what happens if we want to have this for a bound state of Majorana type. So not an electron bound state like what I just discussed, but a bound state of Majorana type. So in the first quantized language, you would have some Schrödinger or Dirac equation. In the second quantized language, this means you have here a Heisenberg operator equation. So the Hamiltonian with C dagger commutes to give the energy of the state times C dagger, or with the annihilation operator, there's a minus sign, minus EC. And now let's try to fulfill these equations with operators that are self-adjoint. So gamma should be the C dagger and the C at the same time. So you see H gamma commutator should be E gamma, but at the same time it should be minus E gamma. The only choice you have to fulfill this is at zero energy relative to some chemical potential. So that tells us Majorana bound states must be zero modes. In fact, since they have an underlying fermionic character, there will be superposition states of electrons and holes. And in fact, we will see their equal weight superpositions of electrons and holes. Yeah. So the natural place to look for such superposition states, sum of electron and hole, is in superconductors, because the BCS quasiparticles that you have in a superconductor are precisely such superpositions of electrons and holes. I should say here as a side remark, this is different from the exciton, which is an electron-hole product state. Yeah? Electron and a hole together bind to give a product state, and this is bosonic in character. Here we have a sum, basically a superposition of electron and hole state, and these can be fermionic in character. Okay. So the next question we want to see is how could we count such strange objects as Majorana bound states or Majorana fermions. So now let's consider a set of Majorana bound states, all of them at different positions in space. Yeah, so each of them will be described by a self-adjoint operator, gamma j is equal to gamma j dagger. And we will require a Clifford algebra for these gamma operators. Namely, if I and j are different, they just anti-commute. It's clear because they are built from fermions, and fermions have to anti-commute. However, if we take the occupation number operator, gamma dagger gamma, for a given Majorana bound state, because gamma dagger is equal to gamma itself, we see that it's gamma squared, and according to this Clifford algebra, you have here a Kronecker delta, this is just 1. Physically, that means you can just annihilate the particle and the antiparticle, and this will not do anything to your state. On the other hand, that also tells you, because gamma dagger gamma is just a number, you cannot use the standard operator for occupation numbers. So gamma dagger cannot serve as an occupation number operator. It's just a number. Doesn't tell you anything, and in fact, it's ill-defined to ask the question, what is the occupation number of a single Majorana bound state? Yeah? So this doesn't work. So you might now conclude there is perhaps no Majorana C. We have a Fermi C, as all of you know, but there seems to be no Majorana C. There is an Icy Outside. This picture is right here from Natal, but I want you to stay inside, so you have to wait for the answer to the question until later. So we can now, however, count the state of pairs of Majorana fermions. So we cannot count a single Majorana fermion, but we can count the occupation state of a pair. Consider two Majorana fermions, gamma 1 and gamma 2, that sit at different positions in space. Then we can form a non-local fermion C. It's non-local because its real part, so to speak, has a different support in space than the imaginary part. So in that sense, it's non-local, it's auxiliary fermion. A priori, it has no physical meaning. But we can use this fermion. It has the correct fermionic algebra. You can easily check. It obeys C dagger plus C dagger C equal to 1. It obeys C square is 0, and so on. So this is a nice fermion. In a sense, Majorana number 1 is its real part, Majorana number 2 is its imaginary part. If you undo the transformation, you see gamma 1 is just C plus C dagger, gamma 2 is basically C minus C dagger, and these operators are Hermitian. Yeah? Gamma 1 is equal to gamma 1 dagger, gamma 2 is equal to gamma 2 dagger. And now you can count the state of this pair of Majorana fermions. Namely, you can define C dagger C as the occupation number of this pair of Majoranas. It has 0 or 1 as eigenvalue. If you multiply out C dagger C, you will get I gamma 1 gamma 2 plus some number. Yeah? So essentially, it is this number I gamma 2 gamma 1 gamma 2, which you can here write as twice the occupation minus 1. So this number here will just be plus or minus 1. And one also refers to this as the parity of this Majorana pair. Namely, it tells you whether this state is occupied or not, so whether there's an even or an odd number of fermions involved. So from this we see that 2 Majoranas equal 1 standard fermion, or 1 Majorana is half a fermion. Yeah, that's the easy rule to remember. A Majorana fermion, a bound state, is half a fermion, and that's in fact the simplest case of a fractionalized zero mode. So the electron basically is splintered into 2 eigenmodes, zero modes. These are good eigenstates of the Hamiltonian, fractionalized, and thereby you have 2 particles, so to speak, that together give you a usual fermion. One point is sometimes overlooked. There is a U1 gauge degree of freedom possible in defining this C fermion. The C is not unique. You could also add a global phase e to the minus I theta, arbitrary phase. You will still have a fermion here, and you get basically a good representation of gamma 1 and gamma 2 again. And we will later use this freedom in choosing this auxiliary fermion to simplify calculations. Another point that is also related to work done by our sleeping organizer, Pasquale. He did some very influential work in the 10 years ago with another of our absent organizers, Gordon Semenoff. It was a paper entitled How to Stretch an Electron as Far as Possible, right? And essentially they were interested in seeing if one could entangle sort of an electron by stretching it into these 2 Majorana fermions. Now, since we cannot count the Majorana fermions themselves, you can also not speak really about entanglement, but you can attach other objects like little quantum dots and then ask, can these be entangled? And in fact, this we recently worked out in a paper with Stefan Plugge, who's also here, and he will give a talk, I think, on Friday on this question, how to generate entanglement through this phenomenon that you can basically stretch out an electron into 2 Majorana fermions, which then live at different positions in space. Okay, so I've already said that we expect that Majorana bound states would live somehow or could be created using superconductors, because superconductors have quasi-particles that are superpositions of electrons and holes. Simplest way would be to use a S-wave BCS superconductor, in which case such BCS quasi-particles are usually superpositions of spin-up particles and spin-down holes. Yeah? Cooper pair is formed by pairing spin-up and spin-down, and also these quasi-particles inherit this property, in which case you have some amplitudes u and v that depend on the quantum numbers, and they have to fulfill a normalization. Absolute value of u square plus absolute value v square must be equal to 1. Now, for instance, if you are at the Fermi level, basically at 0 energy, then the absolute values are identical. Far away from the Fermi level, either u goes to 1 and v to 0, or the other way around. These are electron or hole-like states. Okay? Now, if we try to construct a Majorana state out of this operator, you will see directly this can never work because of the spin. If you take the Hermitian conjugate of that, you will get a C up and a C dagger down. and this can never match, so the spin is really the culprit here. In S-wave superconductors, you cannot generate the Majorana bound state. You have to get rid of the spin in some sense. So we need spinless quasiparticles. And one way to do this is to go for P-wave superconductors, in which case you can have spinless pairing, basically of triplet type. And if now you are at the Fermi level, so that V is essentially the complex conjugate of this U, then you directly see, because there is no spin index anymore, this allows you to create such Majorana operators. The probably best known example for that is the vortex in a two-dimensional P-wave superconductor. It binds such a Majorana bound state, and that's well known. Slightly more recent, it turned out that a more promising route for experiments, at least at the moment, is to use one-dimensional P-wave superconductors, so-called Kitaev chains. These Kitaev chains at their ends will support Majorana bound states, and that's really the route I will describe in some detail here. So these Majorana bound states will emerge as end states of nanowires, essentially, that have superconducting pairing of P-wave type. Yeah? So the Kitaev chain is the simplest model that exhibits these type of states. It's related to the Ising chain, related to what Giuseppe was telling you in the morning. So this model is given here. It's a tight binding chain of spinless fermions. So we have n lattices. On each lattice side, you have a fermion operator Cj with annihilation operator Cj and creation operator Cj dagger. Between nearest neighbors, you have a hopping T. So when hopping, you gain this energy scale T, which we take to be positive. We have a chemical potential term here that is just sensitive to the particle number. And finally, there will be a pairing term. So this is a term that is of P-wave type. So it couples spinless fermions, and it's just nearest neighbor coupling Cj plus 1. So you see there are two annihilation operators, and likewise in the Hermitian conjugate, there are two creation operators. So this describes a proximity-induced pairing gap. In principle, you could ask, there could also be, oh, yes. For now, I need it. I will later talk about what happens if you have a ring or arbitrary boundary conditions. But for now, we have open boundary conditions, a finite length, n sides. So you might wonder, we could also have intrinsic superconductivity, essentially because we might have some coupling to phonons that generate an attractive electron-electron interaction, and thereby generate this type of pairing on the mean field level. Of course, in one dimension, it's tricky to use mean field theory. You shouldn't do that. There's only fluctuating intrinsic superconducting order. But what you can do is you can bring such a one-dimensional system close to a bulk superconductor, and then it will inherit this type of pairing. So this will be our pairing gap, delta. This is taken to be positive real, and then we have a superconducting phase phi that can be arbitrary. Yeah, so that is our toy model. This will describe a one-dimensional P-wave superconductor. Now let's see what we can do about this. We have n lattice sites and open boundary conditions. And to simplify life, first I will consider a special point, delta equal to T, and I will put the chemical potential to 0. So we get rid of this term, and delta is equal to T. In that case, you can immediately solve the whole thing by switching to Majorana fermions again. So we write each of these lattice operators Cj in terms of two Majorana fermions. We can always do that. So for instance, the first lattice side is written as is expressed in terms of a fermion gamma A1 and B1. Yeah, so B1 will be the real part, A1 will be the imaginary part, and I choose this phase here. I told you about this U1 gauge degree of freedom, such that it's just half of the superconductor's phase. That is to just cancel this e to the I phi in that term here. Yeah. So in other words, we have for each lattice side now 2 Majorana fermions. It's completely equivalent. And now you plug this into the Hamiltonian, and that's a 2-line calculation. I was hoping that your schedule is not so dense, so I could give you some homework, but I realized that with a program from 9 to 8, you will not do homework, so I hope maybe when you are at home, you can do this little calculation. It's really very quick. You will arrive for delta equal to t and mu equal to 0 at this result. So if you now look at this, what you have gotten is you couple now the B1 Majorana to the A2. In a sense, you have shifted register. So instead of the original couplings here that defined our lattice fermions, we now see that there is a coupling that sees T times this product, so this parity product and so on. But there are 2 Majorana fermions that do not appear in the Hamiltonian. So these are 0 modes. They commute with the Hamiltonian, gamma left, which is this gamma A1 at the very left end, and there is a B at the very right end. These 2 Majorana fermions do not appear. So they commute with the Hamiltonian. There are 0 modes. They have 0 eigenenergy. Yes? You can map it to a spin chain model, basically Ising model, and then this will turn out to be a ferromagnetic phase, but it's really, it doesn't help much, this mapping here, I would say. It's not a VBS state. Yeah. So to see now why this diagonalizes, we can introduce new D fermions by shifting register explicitly. So instead of the original C fermions, we now just take always these 2 pairs to define the fermion. So for instance, D1 is composed of the B1 Majorana and the A2 Majorana. Yeah, in this way. And since this product, this parity product of 2 Majorana fermions is exactly related to occupation number of this fermion state, which is just plus minus 1, we see that the Hamiltonian here, our Hamiltonian here, becomes precisely equal to this. So we have n-1 new fermions, the D fermions, and you see they sit at finite energy. This energy, delta equal to T, corresponds to the gap of the superconductor. So these are all fermions that live at some finite energy, and in the ground state you will leave these levels all empty. Yeah? They cost energy. They will be gapped. In the middle you have a gap. You have it will not be an eigenstate anymore. Yeah? In general not. So so these are n-1 fermions, and then you have an nth fermion that's this non-local fermion 0 mode that you can make out of this left and out of this right Majorana. So this F, gamma left plus I gamma right half, is now a true 0 mode. It lives at 0 energy, and it's a fermionic 0 mode. Yeah? So this represents our decoupled Majorana bound states at the ends. And now we come to this interesting topological degeneracy, namely, as I said, all the D fermion states with n-1 of them, they must all be empty in the ground state because you have to pay a finite energy T equal to delta to occupy them. However, this non-local fermion, this F fermion, is at 0 energy. You can occupy it without any energy cost, and that means we have a twofold ground state degeneracy in this problem. Namely, we can have an even parity ground state in which you do not occupy the F state. This part here just represents the empty D states. Or you have an odd parity state in which you occupy this F fermion level, so this non-local fermion. And you can construct it out of this by acting with this F dagger. So by acting with a non-local operator on this even parity ground state, you arrive at this odd parity ground state. So we have 2 ground states that differ in fermion parity. That's also called a topological degeneracy, and we can also notice that if we act with the F operator itself onto the even parity ground state, it just kills the whole state. So we can also add it here. F plus F dagger is just the left Majorana, so we can also write this as a Majorana operator acting on the even ground state. So in general, there will be degenerate ground states. With more Majorana firms, you will have a whole manifold of degenerate ground states. And with these Majorana operators, you can now move between these different states in the manifold. So why do I say topological degeneracy? With that, it's meant that we can not distinguish these two ground states by local measurements. What I mean with this is that if I have some local operator, something that only depends on some local support of the chain, it can never detect whether I'm in the even parity or in the odd parity ground state. So the expectation values of this operator will be equal. This holds in general up to exponentially small corrections. If the chain is not long enough, there will be exponentially small corrections, but if the chain is long, you can forget these corrections, and local operator cannot detect the difference between these two ground states. Yeah? Let me briefly sketch the proof. So the local operator is an operator that you can construct in terms of your C dagger and C operators with indices that belong to some finite support. You can also rewrite that in terms of your D fermions. Indices I prime, J prime are basically I and J, maybe up to plus or minus 1. And if the operator has support near a boundary, it might involve the F or F dagger operators. Yeah? But you can always write any local operator in this type of fashion. Now, if this A operator has no support near the boundary, it will not involve the F or F dagger operator. And we now see that the odd parity ground state follows from the even parity ground state by action of gamma left. So if we now go into the right-hand side here and replace the odd ground state by gamma left even ground state, so we have a gamma left, A, gamma left, and then here again the even ground states. But now, since A doesn't contain the gamma left, you can just commute it through and use gamma left square equal to 1, and you have it, both sides are equal. So if the operator is local and has no support near the boundary, both expectation values must be equal. On the other hand, if A has only support, for instance, near the left boundary, it will involve a gamma left operator. And that means now you have a gamma left to the third power here to the first power, but that's equal again. Gamma left to the third is just gamma left. So also in that case, you have the same expectation values. So the message is you can only distinguish these two degenerate ground states with non-local operators. Operators that somehow depend on the entire system, but not with local operators. And that's really a hallmark feature of these Majorana systems. And that also makes them interesting for topological quantum computation, because that also means that noise or decoherence, which is normally a local perturbation, will not be able to change you from the even to the odd parity ground state. So you're, in a sense, topologically protected. Yeah, so you could think of using these two states as basis for your qubit, and local sources of noise will not really be able to switch the state of this qubit. And that's really the basis for what is called topological protection. Okay, just a remark at that point about what happens when we go away from this special point delta equal to t and mu equal to 0. So it turns out this topological phase where you have this degeneracy persists for finite but not too large values of mu. I will come to the precise phase diagram later on, and also arbitrary delta over t. The change that then happens is that this Majorana state is not really at the last site only, so it has a finite extent into the bulk. So it has a finite size, some length scale psi, and typically it's an exponential decay into the bulk. And now if you have a chain of length L, you will have a finite overlap that is typically of the order e to the minus L over xi between these two Majorana states. Yeah? So for finite chain length, we get an overlap of the Majorana wave functions and therefore a hybridization that we will call epsilon f. So what does that mean? It means that instead of a true zero fermion mode here, we have a finite energy mode, but one that is at exponentially small energy. So it's basically a coupling between gamma left and gamma right. We need the I to have a Hermitian operator, and epsilon f here is our hybridization. So you see this is again such a Majorana parity operator, so its eigenvalues are just plus minus epsilon f. Yes, please. At that point, it's an assumption. It depends also a bit on the model. Sometimes it's a Gaussian decay. In some other cases, if the gap vanishes, it can be just power law. But typically, that's what you get. Yeah. Okay, so in general, if it's a finite length chain, this will be a finite energy mode. But in practice now, it depends what is your energy resolution. In the typical experiments, you can easily reach a regime where this L is supposedly large against xi, and you can forget about that. So the true hallmark I would consider for such Majorana systems that would be an experimental signature is the fractional Josephson effect, and that's really a direct consequence of this topological degeneracy. So let me describe this Josephson effect first for the standard case of conventional S-wave BCS superconductors. I hope that most of you or all of you have at some point heard about that, and then we will discuss how this is modified when we have the Josephson effect for two topological superconductors. So the Josephson effect happens if you have two superconductors. These blue bars should be your BCS S-wave superconductors. And you put them at a phase difference phi. So the left one, say, at plus phi half, the other at minus phi half. And now you have a tunnel contact in between. This can be some vacuum or some insulating or even normal metal material. It can be characterized for weak transparency by some tunneling amplitude lambda. Yeah, so that's the amplitude for transferring an electron from left to the right or back. Now, Josephson, he boldly stated in his PhD thesis that if there is a phase gradient, so a phase difference across this junction, there must be an equilibrium current flow, the so-called supercurrent. And he showed that I of phi, the supercurrent flowing in thermal equilibrium, is given by some critical current times sine of phi. So it just depends on the phase difference according to sine phi. So it's 2 pi periodic. And this prefactor, the critical current, is proportional to lambda square. This reflects the fact that you really need to tunnel Cooper pairs. 2 electrons, so for each electron you pay factor lambda, so it's a lambda square in the end. In fact, one can interpret that as the phase derivative of a so-called Josephson energy. Because we are in thermal equilibrium, free energy has a phase-dependent part. This is exactly this Josephson energy with a this Josephson energy with Ej proportional to lambda square as well. So this is this minus Ej cos phi. It's 2 pi periodic, and we get a tunneling of Cooper pairs that then gives us, according to this relation, our Josephson current. Now, what happens if we are in the non-topological case, in the topological case? So now we have 2 Kitaev chains. Let's again, just for simplicity, assume that delta is equal to t. And again, mu is equal to 0, then life is simplest. The algebra is quite easy. And now we know how to describe these finite length chains. These are just Kitaev chains with boundary Majorana fermions at 0 energy. And now we want to connect them by a tunneling, and we want to give them different superconducting phases. So a phase phi left and a phase phi right on that side. And again, we will assume that phi left is phi half and phi right is minus phi half. So how do we connect them? We connect them by electron tunneling. That means there will be a transfer from the right fermion to the left fermion. And right here means the left end of the right one, and left means here the right end of the left one. Yeah? So now we insert the effective low energy form of these operators. Yeah? Because we know the low energy form is completely dominated by this F fermion, by the Majorana bound states. All other states, these D fermions, they sit at finite energy. Yeah? So at low energies compared to the gap, we can project away these states, and we only need to keep in these expressions the Majorana that is the zero mode. So for instance, for the left one, it will only be this gamma B left that we need to keep. That's the gamma left. So if we go into our representation for C left, we see that this gamma A left belongs to the high energy sector. We can forget it. Yeah? So that basically means in the low energy limit, this becomes equal to just gamma left half with this phase factor e to the minus I phi over 4. The same on the right-hand side. Now in that case, it's the A-type fermion that is the one that sits at zero energy, so we need to keep this part. This one can be projected away, and you arrive at this. And now the next step is to insert these two expressions into the tunnel Hamiltonian. It's again a simple exercise, and you see that it will give you products of gamma left and gamma right, and you need the factor I to make it Hermitian. So again, this tunnel Hamiltonian will directly be proportional to the parity of these two Majorana fermions. So it will be something times I gamma left, gamma right. And the prefactor is, you now have to calculate, as a simple calculation, is given by cosine phi half. And that's remarkable because we will see this is a 4 pi periodic function. So it doesn't recover itself after advancing the phase by 2 pi, as you would normally assume. Moreover, the prefactor is not lambda, but not lambda square, but lambda. So both of these things are totally different from the S-wave Josephson junctions. And moreover, we see at low energy scales, this is a conserved quantity, at least within this model. The parity of this junction is conserved. It's plus or minus 1, and it cannot change by anything. So depending on what the parity of the junction is, you have either the plus or the minus sign, and the eigenstates of this Hamiltonian are then given by plus minus lambda half cosine phi half. That's the direct equivalent of the Josephson phase relation of the energy. Yeah, that's this Josephson energy, and you can now get the current from the same relation, and so you will get, depending on which parity you have realized, you get plus or minus lambda times sine of phi half. Okay? So if you sit in a well-defined parity state, and that's a conserved quantity, you just get, for instance, plus lambda sine phi half, and that's a 4 pi periodic Josephson current phase relation. So you have to really advance by 2 cycles to come back. And this really reflects the tunneling of only half a Cooper pair, because you have only 1 lambda here, so tunneling of an electron only. So this is a Josephson effect that proceeds through the single electron tunneling involving the zero mode. It's only possible because you have the zero mode sitting around, and it's highly unusual in that the super current, critical current, is proportional to lambda. And we see that although the original Hamiltonian had a perfect 2 pi periodicity, if you look at the original Hamiltonian of the Kitaev chain, there is nothing that tells you there is 4 pi periodicity. The ground state has only the 4 pi periodicity, because you conserve this parity. So these ground states, the 2 ground states that you have, even or odd parity, will only be recovered when you advance the phase by 4 pi, and not after 2 pi. Of course, for that, this parity conservation is absolutely necessary. Now you have to ask yourself, in physical systems, will I have a chance to have this parity conservation? For instance, we have just considered the boundary states at the contact, but in a finite length for both of these superconductors, you will in general have a finite length, so there might be couplings to the outermost Majorana states. That could give you an effect, so if the chains are not long enough. Or in practice, more important is what one is calling quasi-particle poisoning. By that one means that we have this Andreev or Majorana sector, so these states here. And then far up there is the gap, and you have normal quasi-particles. These are these D fermions I was talking about. Yeah, and we have assumed that these are totally decoupled. We have projected into the low energy sector and assume we cannot have transitions between these two. But in practice, of course, if you are at finite temperature, you will have boson-mediated, for instance, photon-mediated transitions from this sector to above gap quasi-particles. And such processes can flip the parity. And once you flip the parity, you can, of course, restore the 2 pi periodicity. And that's expected to happen at finite temperature in the stationary case. So if you measure DC Josephson current at finite temperature, it will be very hard to see this 4 pi periodicity, if not impossible. But there are proposals how to see it in the AC Josephson effect. So in a time-dependent experiments, you should see traces of that. Okay, any questions up to this point? Yes. In principle, you could think about such processes, but that's a highly irrelevant process in renormalization group language, and it will also be suppressed by additional powers of lambda. So the leading process here is really this term proportional to lambda, which exploits the fact that you have a zero energy resonance. So that allows you to tunnel single electrons. So if it's there, it will always dominate, I think. But of course, in practice, there can be a side effect. In principle, you have both the Cooper pair tunneling and this sort of single electron tunneling in parallel. And then, of course, you have to disentangle what you see in your data. That's zero bias, of course. We are in thermal equilibrium. Once you are out of equilibrium, then it's, of course, even more complicated. You get multiple reflections and so on. Yeah? Okay, so this transparency sort of summarizes what I said earlier about this topological degeneracy. So if you have just a pair of Majorana fermions that are spatially separated, gamma 1 and gamma 2, together they build a zero energy fermion mode. As we have seen, you can store information non-locally in a topologically protected way because we can either occupy this fermion or not occupy it. And no local operators can mix these two states. Yeah? So these two states represent different fermion parities. They're precisely degenerate. And as I said, we have basically a manifold of states now, and we can go between these states by acting with a Majorana operator. Now, if we have more than two, the game becomes much more interesting. In that case, you can see that these Majorana fermions really implement non-abelian anyon statistics, or Ising anyons to be more precise. Since Adi Stern will certainly tell you much more about this in his lectures, I will only show you this one slide about the non-abelian anyons. So for instance, you can think of having 4 Majorana bound states as representing 2 parity qubits. And now think about what happens when you exchange the positions of two of these Majorana fermions. So in this picture, for instance, the blue thing would be the P-wave superconductor, and these red bullets would be the vortices binding each of them a Majorana state, so gamma 1 to gamma 4. And we now think of preparing the system in a state where we do not occupy this fermion and do not occupy this fermion. So we form two parity qubits, one for 1, 2 and one for 3, 4, and we start out from this state 0, 0 in this basis. You see this is a separable state, it's not entangled. And now what we do is we braid these two particles, so we exchange them. Yeah, and look at what happens as we do this operation. And this was investigated in a very nice paper by Ivanov. He showed that this amounts to a matrix acting in this ground state manifold. Explicitly, it can be constructed in this fashion. And if you now remember that gamma 2 flips the occupation number of the 0 here, and gamma 3 the one of the dead 0, you see that this is an entangled state. It's a bell pair made up by 0, 0 plus 1, 1. Yeah, so it's an entangled, maximally entangled state that you have obtained by doing this braiding operation of gamma 2 and gamma 3. And you can represent this as a matrix in the space of these ground states. Yeah? In that case, you will have possibilities, it will be 4-dimensional. Yeah? Now, in that case, it's a matrix in this ground state manifold space. And if you now start to do other braiding operations, for instance, now you exchange 3 and 4, after this 2 and 3, the result will be different if you had first exchanged 3, 4 and then 2, 3. So it depends on how you order these operations, and that's the hallmark of a non-abelian state of matter. So you cannot, it depends on the entire history of what you have done in your braiding operations, and that's again useful in quantum computation. You had a question? Yeah. Yes. Yeah, but that's 2-dimensional in a sense. So you can only do this in 2 dimensions. If you do it with these 1-dimensional wires, you have to build lattices or networks of it, and then you can sort of mimic this. This has been shown in a nice paper by Alicia. So this is really in 2 dimensions specifically. Yeah. But I'm sure that Adi will tell us much more about all of this. Yeah. Okay, so they're not really fermions, as I originally said, but these composite objects, sort of vortex with this bound state, really behaves as a non-abelian anyon, so it is not really a fermion as originally said. But still, the jargon is still to call these beasts Majorana fermions. So that's part 1. I will continue a bit more into part 2. Today. So what this introductory part should have told you is the basic features of these Majorana particles, fermions. So they are fractionalized zero-mode particles. Basically 2 of them make a fermion. We can count their occupation state through these non-local fermions. So by counting the pair occupation of this Majorana bound state, we have seen that in this Kitaev chain, in the simplest case where we have 2 Majorana fermions, we have 2 degenerate ground states that differ in even and odd parity. And basically these are topologically protected in the sense that you can only change between them through non-local operations. We can realize these states as end states of 1-dimensional P-wave superconductors. So the canonical model for that is this Kitaev chain. And we have seen that this will cause a fractional Josephson effect. So at least in theory, that's the, I think, simplest hallmark that is in principle experimentally observable. And they come with non-abelian exchange statistics. Yeah? So that's sort of the elementary background that we will need as we go on. Any questions up to this point? Of course, this I will explain when I come to how one could realize them. They will have a wave function that is sort of carries a spin polarization, but it's nothing you can easily manipulate. Yeah. But of course, then later you can build out of many Majoranas, you can build internal degrees of freedom. This we will learn when we come. But a single Majorana, it's like a single orbital level. You also have no freedom anymore. Yeah. Yes. Doesn't depend on that, no. If n is large enough, basically the bulk will just be gapped. It doesn't matter if you have one or more. At that special point, delta equal to t and mu equal to 0, it's just n equal to 3 or so is already enough. But in general, of course, I told you that there will be a length scale that describes the size of this Majorana bound state. So this is this psi. And what you want is, of course, that this hybridization between both is very small. So the length should be very large against this size of the Majorana bound state. And that's something that's material dependent or parameter dependent. So that, for instance, in this Kitaev problem, the optimal point is delta equal to t and mu equal to 0, then it's really localized. And in the most recent experiments done in the Marcus lab for the realizations, I will tell you, Xi is thought to be of the order 250 nanometers, and they can make wires 1.5 micron long, so factor 6 longer, and then you're basically down to 0 modes. So in part 2 of these lectures, I want to discuss in a bit more detail the Kitaev chain. So in the first part, I will also explain how it relates to the bulk properties of such a one-dimensional system. Namely, we will talk about the so-called bulk boundary correspondence. That's a well-known concept in the physics of topological insulators. So if you have a topologically ordered state of matter, you have a gap in the system, but you have some winding numbers. Basically, you look at the map from the Brillouin zone to the Hilbert space, and this map carries some winding. Yeah? So, and this winding ensures that you have boundary states that are gapless. So inside it looks like an insulator, but on the surface you have basically a metal. These are these strange topological states, and that's this bulk boundary correspondence. We have edge states, or in our case, for this P-wave superconductor, you have a bulk gap, but you have gapless or zero energy end states. These are the Majorana end states. And this winding, you can only see basically in the Brillouin zone, so you need to go to a ring, to periodic boundary conditions. So the question is, what is the phase diagram of this Kitaev chain if you look at the periodic system? So if you take it on a ring, and then somehow these end states should only appear when you are in a topological region of parameter space, so where you have these strange winding properties in the map from Brillouin zone to Hilbert space. And in fact, we will see that in that case, we can define a topological index. In this model, it's of class C2. So C2 means it's either +1 or 0 or -1. So there are two possibilities. Either it's trivial, isomorphic, or adiabatically connected to vacuum, or it is non-trivial, and then it's topological and has these Majorana end states. That's all there is. And if we are in this topological state, then we will see that there is in fact a sensitivity of the ground state to boundary conditions. It's again a hallmark of non-locality. Yeah, if the ground state really depends on what kind of boundary conditions you impose, that really tells you you are with almost certainty in a topological state. So this is what I want to discuss. The first half of this part, probably that will be all for today. And then in the second part of this part 2, I will discuss in detail how you can realize this Kitaev chain, this simple toy model that Kitaev suggested in 2001 in the lab. 2010, there were 2 very nice papers that showed or predicted that you can realize this in practice using semiconductor nanowires, indium arsenide, indium antimonide. They have strong spin-orbit coupling. You need also a Zeeman field, so magnetic field, and you need to proximity couple this to conventional S-wave superconductors. All of these are ingredients that people had readily in their labs, so within 1 or 2 years already the first science papers came out reporting Majorana fermions, and I will briefly discuss also that. Yeah. So my main focus in these lectures is on the theoretical concepts, not so much on the experiments, but I will briefly discuss some of these experiments also. Okay, so that's the plan. So as I said, the Majorana bound states for the open boundary conditions should mirror some bulk topological features. So let's consider now the Kitaev model on a ring. So we impose periodic boundary conditions instead of open boundary conditions. Yeah, and here I will allow arbitrary parameters, not just delta equal to t and so on. So once we are on a ring, we have a conserved momentum k, which means we can, or it pays off to switch from the lattice operators in real space to k space, to momentum space. So I give this a tilde to distinguish the ck in momentum space from the real space operators. And then you just have k's in the first Brillouin zone. In this one-dimensional system, I take the lattice constant to 1. So the first Brillouin zone goes from -π to +π. And we have precisely n momenta in this first Brillouin zone. And you get the Cj out of the Ck by essentially a discrete Fourier series. So for index j here, you have e to the ikj, and you sum over k. Okay, now it's also common in the business of superconductors to form these Nambu spinors to simplify how these equations look like. So in a Nambu spinor, you combine in the upper part the particle annihilation operator and here the hole annihilation operator. Hole annihilation means particle creation. So here you have a Ck, here you have a C dagger of -k. Yeah? It's a time-reversed partner of the particle. And now if you take this definition here and plug it into our Kitaev chain, but now with periodic boundary conditions, so you have to go with the sum such that you go across the ring. If you plug this in, it's again a simple calculation, and you will find this Hamiltonian. The factor 1/2 is because otherwise you would have double counting, because you get C dagger terms from this here and here. Interpretation is here you have a kinetic energy for electrons. Here you have a kinetic energy for holes. That's exactly -ψk. So this kinetic energy for our band electrons is just -t cosine k minus the chemical potential. So that's that. And you see this is an even function of k. Now the pairing, so this term here, will be off-diagonal in this representation because it will mix Ck with C minus k and C dagger with C dagger minus k. Okay, and you have here the Fourier transformed p-wave pairing potential. So with this original parameter delta and the phase phi, you see it's proportional to sine of k. That's important. It's odd in k, and that's the hallmark of p-wave. P-wave orbitals, they change sign as you go through the zero. And you see here, this is antisymmetric in k. As you change k to -k, you get a minus sign. So that's really a p-wave pairing. That's why one says the Kitaev chain is a p-wave superconductor. Okay, so now you see already here that the sum over different k's completely decouples. That's an important point because now we can solve this problem for each case separately. And it will boil down to a diagonalization of a simple 2 by 2 matrix. And this 2 by 2 matrix is also called the Bogoliubov-Degenn Hamiltonian, by the gentlemen's names who have first used this type of trick with Nambu spinors. So it's a 2 by 2 matrix in this particle hole space. And to diagonalize this, you have to make a rotation in this particle hole space. It's also called a Bogoliubov rotation. Yeah? So the diagonalization means that we have to find the eigenenergies and the eigenvectors of this 2 by 2 matrix. So we have to solve basically this eigenvalue problem. It's a simple problem. You find two eigenenergies plus or minus square root xi square plus delta square. Why do I omit the minus solution? It's simply because of this factor 1/2. If you write out what you get from the minus solution, it is exactly the same as the one from the plus solution. So it would be just an overcounting to keep that. So we just keep the positive sign, and we see therefore that these particles in the diagonalized basis, which you get as superpositions of electrons and holes, with the components just given from the eigenvectors of the solution of this 2 by 2 matrix problem. Yeah? So these are exactly our BCS quasi-particles, but now for P-wave. This is the BCS quasi-particle spectrum. And here you have explicit forms that solve this eigenvalue equation, the so-called BDG equation. Very nice. So now you see this is positive. Seems to be always positive. No, it will not. There will be zeros in that. And that will be very important because the general rationale for looking for the phase diagram is that once you're in a gapped phase, you need to close the gap to get into another gapped phase. Yeah? So we will first look for the gap closing points of this dispersion relation. Whenever this gap closes, 0. Yeah. So we have to look, does this energy have a chance to reach 0? In that case, you can have different phases on both sides. So that's typical. You might have a trivial phase that is related to vacuum, and you might have one of these topologically non-trivial phases that when you have a finite boundary, it will have these Majorana states. So when can this beast be 0? Of course, we need both the xi k to be 0, and we need the delta to be 0. So let's have a look at their expressions. Delta equal to 0, we can do this for k equal to 0, but we can also do it at the zone boundary. The Brillouin zone boundary is at pi or minus pi, which is the same. Yeah, they just differ by a reciprocal lattice vector. So that means at k equals 0 and k equal pi, we have a chance to close the gap. Now let's look at the first expression. This also has to be 0, otherwise we will still have a gapped phase. So if k is 0, we have here minus t minus mu. So that means for mu equal to minus t, the gap will close. At k equals 0. At k equal pi, it will close at mu equal to plus t. Yeah, so we have these two possibilities. So the energy of these excitations vanishes. So we have a gap closing. Topological phase transitions require such a gap closing, and this happens indeed at these 2 points. So that tells us that we have 3 different regions. One is mu less than minus t, one is mu bigger than plus t, and then in between. Now these 2 phases really are the same. They're related by electron-hole symmetry, and in fact they're topologically trivial, so-called strong pairing phase of this model. Why is this topologically trivial? Anywhere in this region you can change parameters without really changing the topological topological features, because these are really winding numbers. You cannot change them in little quantities. Either you have this number or you don't. Yeah? So if we change mu, for instance, smoothly from some value larger than t all the way up to infinity, if mu is infinity, there's no particle anymore possible, so you have vacuum. So this phase must be related to vacuum adiabatically, and likewise the phase with mu less than minus t. So in between, on the other hand, we would expect to find a topologically non-trivial, the so-called weak pairing regime that will then have Majorana bound states when you have open boundary conditions. In fact, that contains our point with mu equal to 0, which I have considered before for the construction of these sites. So the expectation is that indeed chemical potential absolute value less than this T will already give us this topologically non-trivial phase for arbitrary delta. Now, how can one really see that? And how can we construct a C2 invariant? So a topological number that really is +1 or -1. If it's -1, it will be the topological phase. If it's +1, it will be trivial and has no Majorana end states. So let me describe this. And a nice way to see this is to think of this BDG Hamiltonian as a spin in this Nambu space. Nambu space is a 2x2 space, so in a sense you can think of it as a spin moving in a magnetic field. Tau here, the vector of tau means Pauli matrices tau x, tau y, tau z. So for instance, if we look at our BDG Hamiltonian, the tau z matrix here you look at the diagonal, so the z component of your magnetic field is just psi k, it's just this kinetic energy. While here the off-diagonal parts probe the tau x and the tau y matrix. And you will see these are antisymmetric under reversal of k, while this is symmetric under reversal of k. So that's in fact a direct consequence of particle hole symmetry. So these fields, if they are subject to particle hole symmetry, as they have to be in a BDG Hamiltonian, they have to satisfy these symmetry relations. That tells us we only need the field for the half of the Brillouin zone from k equals 0 up to k equal pi. Okay? So now I told you these topological features basically come from winding numbers when you look at a map from the Brillouin zone to the space of Hamiltonians or to the Hilbert space. So in that case, it will be a map from K, the Brillouin zone in this region, to the unit sphere that is given by the magnetic field here. So you take the magnetic field vector here and divide by its absolute value. So this will span a unit sphere on which this magnetic field direction moves. And now we know that at 0, k equals 0, and at the zone boundary, this delta function just vanishes. So this B field is completely aligned along the z-axis. It can be either at the plus or at the minus z-axis. So it is S0 or S pi times z at k equals 0 and k equal pi, where this S0 and S pi is just plus or minus 1, depending on the sign of the kinetic energy at the respective k. Okay? So what we know now, it's at k equals 0, we start, for instance, at the North Pole, and now we ask what happens as we change k. We go from k equals 0 to pi. And now there are two possibilities. Either the field stays near the same pole. That's basically you start out at the North Pole and you end at the North Pole at pi. And in between you might move a little bit around here, but you could contract that back to a single point. On the other hand, a non-trivial phase really explores the whole sphere because it must go from the North to the South Pole as you traverse the Brillouin zone. So this topological index or C2 invariant for the bulk case, for the periodic boundary condition case, is simply the product of these two numbers, S0 as pi, and you get this from the sign of the kinetic energies here. So that's the phase diagram of this Kitaev chain. As chemical potential is bigger than T or less than minus T, you have a non-topological strong pairing phase where you either stay at the North or at the South Pole only, and nu is equal to +1. And in between, so if the chemical potential is between minus T and plus T, you're in the topological weak pairing phase, and you go from North to South Pole or back. Yeah, so you have to explore the the sphere during this motion from k equals 0 to k equal pi. So the ground state of this periodic boundary condition problem we can now get from elementary derivation. And just to use different language, I avoid the Nambu language here and rewrite it just in terms of our CK operators. So we see that for finite k, and I should say this is assuming that the chemical potential is close to the transition at minus t. So we take here only the positive k and write out the negative partner state explicitly. Since psi k, the kinetic energy is even in k, we just get that. And the pairing here, you pair ck with c minus k. And we see that these k minus k pairs completely decouple. So we can solve for each of these pairs individually. So what you do is you expand this using basis states nk and n minus k. Nk is the fermion number for this state ck, plus 0 or 1, 0 and 1. So in principle there are 4 basis states, but you can cut down the workload even more because the even and odd parity sectors decouple once again. So for given k, in the even parity sector we have basis states 0, 0 and 1, 1. So either we have both the k and the minus k state empty, or both of them occupied. If they're both empty, you can't get pairing, but you also don't get any kinetic energy, that's this 0. If both are occupied, you just get twice this psi k, and the off-diagonal terms here then give you the pairing. So that's in the even parity sector, and you can readily diagonalize this 2 by 2 matrix. You find 2 eigenvalues for the energy, it's psi k plus or minus our square root. That's exactly this energy of the quasi-particles that we had so far. In the odd parity sector, you have the basis states 0, 1 and 1, 0. And you see now in that case pairing cannot give you anything. You need 2 particles or 0 to get the pairing. And it's just diagonal and the energy is just psi k. So what does that tell us? It tells us that the ground state will necessarily be in the even parity sector here, because you can lower the energy with this minus sign here. And that means the lowest energy here has even parity with this minus sign, and the UK and VK then follow just from the eigen vectors of this solution. So the ground state will have a part from the k modes that are different from 0 that looks like this, and it's even parity. But we still have this k equals 0 mode in the center of the Brillouin zone, and since the delta is 0, the p-wave superconducting pairing amplitude vanishes here with just the kinetic energy here, yeah? Psi at k equals 0. And now you can see that we have this k equals 0 unpaired fermion mode at the energy minus t minus mu. And now if mu is bigger than minus t, this thing here is negative, and that means you will occupy that state in the ground state. So that means the ground state has odd parity, and it's not degenerate. Yeah? It was degenerate with open boundary conditions, but here it's unique. It has odd parity because you occupy this mode. On the other hand, had you started with antiperiodic boundary conditions, there is no k equals 0 mode from the start, and that means you would have an even parity ground state. So in other words, there is a strong sensitivity to what kind of boundary conditions you impose on your system. Periodic or antiperiodic boundary conditions give you a different ground state parity. That's a hallmark of a topologically non-trivial phase, such as sensitivity to choice of boundary conditions. In the phase that mu is less than minus t, that's the topologically trivial phase, it doesn't matter at all. The state is always at positive energy. It doesn't matter whether you occupy, it's always unoccupied, and it doesn't matter whether you have periodic or antiperiodic boundary conditions. So that's really a hallmark. And in fact, you can interpolate between these two boundary conditions by taking a ring, this Kitaev ring, and now you take one link, replace the hopping amplitude by some lambda, some weak hopping basically. If lambda is 0, you are back to the open boundary condition, so finite chain link, a finite length chain. If lambda is equal to plus t, you have your periodic boundary conditions. If lambda is equal to minus t, you have anti-periodic boundary conditions. And now, if we start with anti-periodic boundary conditions at minus t, we see we have an even parity ground state, and the odd parity ground state is separated by a gap. On the other hand, if you end up at plus t, it's the other way around. So the odd parity ground state is the ground state, and the even parity one is at finite gap upstairs. So as you change lambda, you have something where you move like this. You must cross at some intermediate value, and at that point, both these parities have the same energy. So that's exactly this, in this case, exactly the open boundary condition case, where you have the Majorana n states ensuring that you have this topological degeneracy. Yeah? So that's, I think, a good point to stop. In the next lecture, I will then discuss how to really realize this Kitaev chain, and we will move towards interactions and topological Kondo, but that's sort of the basics. Thank you.